And we're back at it again. I'm going to try to finish up the chapter today. So, if we start in section 22.7, it talks about synthetic strategies for making amines. And this is just a review of what we talked about in the previous lecture. We have the old ways of making amines. That's the reduction of amides. Talked about that in the carboxylic acid chapter. You use lithium aluminum hydride to reduce down amides. We've talked about the reduction of nitriles. Again, you can use lithium aluminum hydride to reduce nitriles to amines. And then finally, we can reduce down nitro groups, which we talked about in the aromatic chapter, and those produce anilines. So the new ways to produce amines are really based on old chemistry that we've seen before. The Gabriel amine synthesis, which relies on a SN2 reaction. And notice that is exclusively for producing primary amines. You can use the azide synthesis, which is also a SN2 reaction. And again, exclusively for producing primary amines. And then the most functional one is the reductive amination, mixing an amine with a carbonyl in a one-pot reaction in the presence of a reducing agent. The one that we tend to choose is the sodium cyanoborohydride. And from it, you can produce primary amines. If you happen to take a primary amine and a carbonyl and mix those together in the same conditions, you would get an imine that is reduced by the sodium cyanoborohydride to get you a secondary amine. And if you took a secondary amine with a carbonyl, again with the reducing agent, the sodium cyanoborohydride, you would end up getting an iminium ion or an enamine. Either way, those are reduced down to a tertiary amine. And then finally, if you wanted a quaternary ammonium ion, you could just alkylate again. There's a quicker way to do that alkylation reaction, and that's simply just to take ammonia plus an excess of the alkyl halide. And that would add, and you would end up getting a quaternary ammonium ion out of that. So those are all the new and old reactions that we've seen to make amines. Now that we've talked about making amines, we're going to look at reactions of amines. As I keep mentioning, most of this is review. We've seen all this chemistry before. So the reactions of amines, we can acylate them, meaning we can react them with a acid chloride or even an anhydride or even an ester and make amides. And what's interesting about this is it's somewhat circular, because from the amide, if we took lithium aluminum hydride, we could also make an amine. So from acid chlorides with ammonia, we can make a primary amine. In the second example here, with an acid chloride in the presence of a primary amine, we can make an amide that we could then go on and make a secondary amine from an acid chloride and a secondary amine. We could mix those together to make an amide that we could also reduce down to make a tertiary amine. Now, in all these cases, we have to use an excess of the amine, and hopefully you remember why. And if not, I'll remind you that the second equivalent of the amine is used as a base to deprotonate the product in this reaction. Now we can actually use these acyl groups as protecting groups. And we can do that because it is possible to hydrolyze amides. Again, we're seeing chemistry that we've talked about before. If we took a amide in the presence of acid, we could hydrolyze that back to the carboxylic acid, which is what we talked about in the carboxylic acid chapter. But in this one, we could look at it in a different way and say that we actually want to deprotect our amine. Since we're under acidic conditions, we actually would get a positive ammonium in this case. But if you notice, what we could do is we could protect our amine, and then if we hydrolyze it, we could deprotect it. So in some cases, it may be advantageous to actually protect amine to avoid unwanted side reactions. And here are some examples of those reactions. In the top right, if I wanted to get a single Br on this aniline, it'd be somewhat problematic. And the reason for that is this nitrogen is donating its electrons in. It's an electron donating group, and makes this a very good nucleophile. Typically, aromatic rings aren't very good nucleophiles, but anilines are especially electron rich. And in fact, if I add bromine, notice I don't even need a catalyst. So I don't have a catalyst in here, and I get a tribromination on there. So I can't avoid that polysubstitution. So what I could do is protect that amine and convert it from a strong electron withdrawing group into a moderate electron. Oh, let me strike that, reverse it. A strong electron donating group. I convert it from a strong electron donating group into a moderate electron donating group. So it doesn't activate the ring as much. And so when I mix it with bromine, again, I don't need a catalyst here because it's still activated enough. It's only going to add one bromine. And once I put that bromine on, the bromine acts as the electron withdrawing group, makes the ring less nucleophilic, so I only add once. But again, I still want this aniline here, and I've got this pesky acyl group. So to get rid of that acyl group, I can hydrolyze either under basic conditions or under acidic conditions. Again, just the hydrolysis of amides is chemistry talked about in the carboxylic acid chapter. So nothing really new there. Something else that it can do is it can allow us to do Friedel-Crafts alkylations and Friedel-Crafts acylations. So again, if I wanted to do this reaction in the top right here, I would have problems. Remember back to the aromatic chapter, I always said, try not to do reactions with amines. Make sure that the amine was the last step. So you'd reduce a nitro group to form the amine, and in essence, trying to do electrophilic aromatic substitution reactions on anilines was always problematic. And one reason for that is they're such good nucleophiles, and so they would undergo a Lewis base, Lewis acid reaction, form this adduct here that is now deactivated. And since it's deactivated, you can't do Friedel-Crafts on deactivated rings. Notice there's a positive right next to the ring. So this is no longer a good nucleophile. This would be a very poor nucleophile, and we couldn't use it for Friedel-Crafts alkylations. So what we can do is we can make this into a protected ortho-para directing group by acylating. And so in short, we would just undergo an acylation reaction. You'd either need a base or our excess of the amine to get this to go. But overall, the transformation that you'd want is to put an acyl group on there, and now we have a moderate director. And we've also protected our nitrogen. So no longer will it react with the Lewis acid catalyst in here, and we can actually do a electrophilic aromatic substitution. In short, the electrons would come out and grab the positive of that CH3 and then would re-aromatize. And again, if I wanted to actually make this one here, which is known as para-toluidine, I would then throw in a base or acid and hydrolyze that amide, and I would have my amine. So this is the third protecting group that we've seen. Back in alcohols, we had the TMS protecting group. In the aldehyde ketone chapter, we had acetals that served as protecting groups, and you can actually have these acyl that serve as protecting groups of amines. So here is just another example where we're trying to do a Friedel-Crafts acylation. We're trying to make this molecule at the end. We're trying to add this group. And again, I wouldn't be able to add that group directly with a free amine. So what I need to do is to protect the amine. In this case here, they're actually going to use the acetic anhydride. And again, similar reactivity to acid chlorides. We're going to use pyridine as the base to soak up the protons. And we can protect the aniline there. And once we've protected the aniline, then we can actually take our benzyl chloride, which is the group that we want to add to the ring. We take the Friedel-Crafts acylation catalyst. And there's another advantage to having this amide here, and that is that it's going to sterically hinder the ortho positions, and it's going to favor the para positions. And so we would expect adding this benzoyl group to our para position. And then finally, we need to get rid of the protecting group. And in this case, they decided just to use a base hydrolysis. And so that OH minus would come in, up, down, and kick out those electrons, breaking that bond right there and revealing your amine. So this is another example of protecting group chemistry that allows us to do reactions that we would have problems with otherwise. Now I'm going to really fly through this section here. This is just more FYI. So we've always had this issue of the Hoffman product. We had the Zaitsev product, and then we had the Hoffman product. The Hoffman product tended to be the less substituted double bond, and the Zaitsev product ended up being the more substituted double bond. And so the question is, well, where did this idea of the Hoffman product come from? And so the idea of the Hoffman product came from this reaction right here. And so just to run you through it, like I said, this is just more to help you understand and why what the Hoffman product is and where this discovery was made. So what they do is they take an amine and they exhaustively methylate it, meaning they add as many methyl groups as they can, and they convert it into an ammonium ion. And once you convert it into the ammonium ion, you actually have a positive nitrogen, which is an okay leaving group. And in this reaction here, what they do is essentially an E2. So the overall transformation is we convert that amine into a leaving group, and we're going to do an E2 elimination. And in any E2 elimination, if we have two different types of beta hydrogens, so here we've got some beta hydrogens in red, here we've got some beta hydrogens, oh, sorry, let's write the beta hydrogens in red and beta hydrogens in blue. So we could form two different double bonds. And you notice in this reaction here, we tend to form the less substituted double bond, which we know as the Hofmann product. And it's because of this reaction that it is known as the Hofmann product. So if we look at this example in the middle there, we've got red protons that if we removed would give us a more substituted double bond. We've got green protons that if we remove would give us the less substituted double bond. And you can see in this example here that we actually favor the less substituted double bond, and that is what's known as the Hofmann elimination. So to sum it up, we can do elimination reactions. We did lots of them with alcohols. You can also do them with amines. To get the amine to eliminate, well, let's back up. To get the alcohol to eliminate, we typically turned it into a tosyl group. There were other ways, such as mixing it with sulfuric acid, but we turned it into a tosyl group, and then we could do an elimination. For the amine, what we do is we convert it into an ammonium ion, meaning we add as many alkyl groups to it as possible. And so in this case, we're adding 3 alkyl groups, and that ends up with a positive nitrogen, which makes it into a decent leaving group. And then just a little bit about the interesting reagents that they use. They use this silver oxide and water. Now, since nitrogen's positive, it needs a counter ion, and that counter ion is going to be a halide, in this case, iodide. And so iodide and silver, they form a very strong complex. They tend to be insoluble in water. Remember your Gen Chem solubility rules. Silver halides were insoluble. And so what happens when you mix this silver oxide and water, it actually pulls out the silver halide as a solid and replaces the counter ion with a hydroxide. And so you get this ammonium hydroxide. And when you heat that up, even though this is a small base, it tends to pull the proton off of the more accessible side. And there's lots of reasons for that we could talk about, including looking at the Fischer projections. And we're going to avoid looking at the Fischer projections, because again, this is really just to help you understand what the Hofmann elimination is, and to remind you that the Hofmann elimination favors the less substituted double bond. For those of you that want to know, to get the more substituted double bond, you still need an anti-periplanar H. And in order to get that anti-periplanar H, you would have to put these large groups adjacent to each other, and that gives rise to some steric interference. So in the Hofmann elimination, you tend to pull off the more accessible proton, and that allows these groups, these large groups, to avoid some steric clashes. So a lot of what drives the Hofmann elimination is sterics. So again, you've got a small base, but it tends to pull the proton off the most accessible carbon to give you the less substituted double bond, which is the whole take-home message for the Hofmann elimination. Okay, let's just fly past the Hofmann. So what you need to know out of the Hofmann elimination is that it forms the less substituted double bond, and what the reagents are, and just how to identify where that less substituted double bond is. So the last set of reactions that we're going to look at that amines undergo are reactions with nitrous acid. So we've used nitric acid before, which is HNO3. It's one of those strong acids that you memorize. It's very good at oxidizing. We've seen it in reactions back in the aromatic chapter. We used it to nitrate aromatic rings. We're going to focus on a different acid that is known as nitrous acid. HNO2, or if you say it as its formula, it is also known as HONO or HONO. Now you can actually generate nitrous acid by taking a salt, sodium nitrite, and mixing it with an acid, HCl. And so the mechanism for that is we simply take the nitrite and protonate it. And when we do, that generates this nitrous acid. Now, in the presence of that acid, we can protonate it again. And when we protonated it again, like it shows down here, protonated nitrous acid, that water can leave. And we did this very similar reaction to nitric acid. In nitric acid, what we did is we generated the nitronium ion. The nitronium ion was the species that we added to aromatic rings. So we're going to do a very similar reaction here. We're going to protonate nitrous acid. The water is going to leave, and what we're going to generate is the nitrosonium ion. And the nitrosonium ion has these two resonance forms. So you could have a lack of an octet at that nitrogen there, or you could have this resonance form where those electrons would feed in. Now, in the right example, everyone has an octet, but the oxygen has a positive. Either one of these would be valid in a mechanism, but overall, what's going to happen is this nitrogen right here is going to be very electrophilic, and this nitrogen here is going to be very electrophilic. Again, very similar to what we did with the nitronium ion, is we pushed nucleophiles into the nitronium ion up here in the box, but we're going to do it in the nitrosonium ion, and we're going to use nucleophiles. And so we're going to use specifically nitrogen nucleophiles. So what happens when you have a primary or secondary amine, an N-nitrosamine is initially formed. And so up here, what we've got is a secondary amine, and if you had sodium nitrite and a little bit of acid, you get an N-nitrosamine. Now, if you read the ingredients on hot dogs, you'll see that many of them now say that they're nitrite-free. And the reason that they're nitrite-free is because if you had nitrites in your, and they're typically used as preservatives for meat, and you ate the hot dog and introduced it into your stomach with some hydrochloric acid, you would form this nitrosonium ion that would then react with secondary amines in your body and give you this N-nitrosamine. And these N-nitrosamines are known to be carcinogenic. So we'll look at some of those examples in just a second, but let's look at the mechanism. So the mechanism, just as we did on the previous page, we're going to generate this nitrosonium ion that has these resonance structures here. And then it's a simple mechanism where the nitrogen will come in and attack the nitrogen of the nitrosonium ion. You could also have it attack this resonance form there and kick the electrons up onto the oxygen. No matter which way you choose, you're going to end up with this intermediate right there, this N-nitrosamine that is protonated. And then simply we just need to deprotonate that so we get this neutral species. So we end up with a nitrogen to oxygen double bond compound, and again known as N-nitrosamines. So we have some interesting ones that are found, and again these tend to be carcinogenic. So these tend to be found in food products including cured meat, fish, and beer. This is found in fried bacon and found in tobacco smoke. And again, these things tend to be carcinogenic. So that's why they tell you to limit the amount of fried foods. And again, why hot dogs advertise that they're nitrite free. So that's if you have secondary amines, we end up with these N-nitrosamines. Okay, now primary amines initially give you an N-nitrosamine, but then they undergo a further reaction. So notice up here that we're dealing with a primary amine, but the end product that we get looks very different than just a N-nitrosamine. So we don't just end up at this product here. There's some more chemistry that goes on that converts it into these diazoniums. And I'll give you a hint that the reason that we can continue on with the chemistry is due to the fact that primary amines have 2 hydrogens. Secondary amines only have 1 hydrogen, and so we stop. Primary amines have 2 hydrogens, so we can continue on the chemistry. So let's look at how this works. So again, we're going to generate the nitrosonium ion, like we talked about before. You protonate the sodium nitrite, and eventually water just leaves. This first step is exactly the same that we saw with secondary amines. We're going to attack the nitrosonium ion, and then we're going to deprotonate. And like I said, we're going to end up with an N-nitrosamine. But if this was a secondary carbon, we would stop. So if that was an R there, then that would be the final product, and we would be done. But it's not. There's a hydrogen there, and we're in the presence of acidic water, and so what happens is this reaction continues. So just like we've done before in the ketone aldehyde chapter, we protonate that carbonyl. And when we protonate that carbonyl, what we can do is actually deprotonate the nitrogen. Again, as I mentioned, this hydrogen is key for this further reaction, and those electrons drop down and we kick those electrons out. So this should look very similar to chemistry that we just talked about. If not, a little drinking or squinting will help you realize that that looks an awful lot like an enol. The difference is, instead of a carbon-carbon double bond, you have a nitrogen-nitrogen double bond. And so what you could do is you could say that this reaction is just an enolization under acidic conditions. So in fact, if you look at the reaction to do an enolization under acidic conditions, it's exactly the same. What you do is you would start with a carbonyl. That carbonyl would get protonated. Once we've protonated that carbonyl, we have a hydrogen here. Some base would pull off that hydrogen, collapse those down, and what we want to do is get rid of that positive on that oxygen, and that would give us our enol. So the arrow flow here, the electron flow, is exactly the same as an acid catalyzed enolization reaction. But we're going to do it with this interesting N-nitrosamine. So protonate it, enolize it, and then we end up with this interesting group. Now, we don't just stop there either. Notice we've got a lone pair here. And that lone pair is going to be key, because what we're going to do is deprotonate and convert that OH into a good leaving group. And once that's a good leaving group, the lone pair from that nitrogen is going to drop in and kick out the water. And so what's driving this is the strength of nitrogen-nitrogen triple bonds. They're very, very strong. N2 is a very stable molecule. It's a gas, it makes up 80% of what you inhale, and there's just a lot of strength in those bonds. So that's what's driving this reaction, as well as entropy when you lose water. So you end up with this, what they refer to as a diazonium. Azo coming from the name for dinitrogen compounds, so it's a diazonium. And since it's charged, you're going to have some type of counter ion there. Okay, so with alkyl diazonium salts, so we get this diazonium compound right here. So if you take sodium nitrite and HCl, you'll get this diazonium salt. And again, if you want to know the mechanism, it's that whole process down there at the bottom. Now, alkyl diazonium salts aren't very stable. Again, this N triple bond, which is kind of driving this reaction, is a very good leaving group. It's actually N2, so it could just leave as N2 gas and leave behind carbocations that can undergo rearrangements. So alkyl diazonium salts are extremely reactive, potentially explosive. So if you try to isolate these in the lab, just like azides, they tend to explode. And they explode by releasing N2 gas. So there's not much use. So why did we run through all this? Because for primary amines, this reaction with nitrous acid is of no use other than ridding yourselves of potential enemies, or in the zombie apocalypse, maybe making bombs. So there's really no synthetic utility for these alkyl diazonium salts. So we spent time talking about it because there are other types of primary amines, and those are aromatic amines, also known as anilines, that can undergo the exact same reaction. So down here at the bottom, we have essentially a primary amine, aniline. It can undergo a reaction with NaNO2, sodium nitrite, in HCl, to form this aryl diazonium salt. And again, if you want to know the mechanism here, the mechanism is exactly the same here. Notice that this R could be an aromatic ring. And so when we get this diazonium, it is stabilized. You don't want to heat them up too much, but there's a reason that the nitrogen just doesn't leave here like it does on alkyl groups. And that's because if it did leave, it would leave behind a positive on an sp2 carbon. And positives on sp2 carbons are not very stable. This is a positive, and actually this is not really an sp2 carbon. Once that nitrogen leaves, it actually becomes an sp carbon. Once the nitrogen leaves here, it becomes an sp2 carbon. So if this is sp2 carbon, carbocation, it actually has, sorry, I'm trying to do math, 33% S character. And if this here is an sp carbocation, it has 50% S character. And remember, S character is good for helping us hold negatives, but it's bad if we have lots of positives. More S character means that those orbitals are closer to the nucleus. And so this positive here, that's essentially an sp orbital, is very unstable because we have a lack of electrons in orbitals that are very close to the nucleus, which is positive. So the take-home message is aromatic carbocations or phenylcarbocations are too high in energy to form. So in this case here, the nitrogen just doesn't get up and leave. So this right here we can make. And that's cool that we can make it. And like I said, if you heat it up too high, it actually will undergo a bunch of other reactions. But if we treat it nice, we can do a whole set of interesting reactions with that aryl diazonium salt. And these reactions are known as the Sandmeyer reactions. So the actual Sandmeyer reaction we don't need to know. You should know how to get to this aryl diazonium salt right here. There's other ways to generate the nitrosonium ion. And in this case here, they're just using HONO. So they actually have nitrous acid, and then they're just using a strong acid. And overall, the transformation would just be to make this nitrosonium ion. Again, a little bit more common way is to use sodium nitrite plus HCl. And it will also generate this nitrosonium ion. So you should know the mechanism definitely for this step here. And once you have made that diazonium, what you can do is you can throw in a bunch of these copper 1 salts, either copper 1 bromide, and poof, it will replace this diazonium with bromide. We'll throw in copper chloride. Poof, it replaces the diazonium with a chloride. Well, let's try copper iodide. Poof, it replaces it with an iodide. Hey, let's throw in copper cyanide, and poof. So for all of these steps, thought to be radical or very complex mechanisms. So you don't need to know the mechanisms, but you do need to know the products of these reactions. So these Sandmeyer reactions are very versatile. Once you make that diazonium, you can undergo a lot of transformations. You can put a bromine on there. And we were able to put a bromine on there previously, as well as chlorides and iodides as well. This just gives us another tool in our synthetic tool belt. Before we could use BR2 and FeBr3. But this is another route, and it actually opens up some possibilities for aromatic synthesis that we couldn't do before. So again, these are known as the Sandmeyer reactions. So first of all, you make the diazonium. So again, we know the mechanism for this. And then for this second step, when we're just replacing that diazonium with group X, is just kind of poof. And so there's some other transformations that we can make. If you throw in HBF4, you can actually put a fluoride on there, which we haven't been able to do before. If you just throw in H2O and heat, you can actually make a phenol. And this is really the first synthetically useful way that we've had to make a phenol. There was an example back in the aromatic chapter about oxidizing cumene to make acetone and phenols, but we never really stressed that because it's not really a synthetically useful way. So if you need to make a phenol and you see an OH off there, here is your route to do that. And then finally, you can take a diazonium salt, you can take H3PO2, and you can actually just make that diazonium disappear. You may wonder, well, why would I go through all the work of putting a nitrogen on there, making the diazonium, and then making it disappear? And sometimes you need it for directing effects. So sometimes you need that nitrogen to direct, and then you just want to make it appear or disappear. So we have that option. So these Sandmeyer reactions, very useful because from just the diazonium, we can get to a variety of different aromatic substituents. And so I've summarized those here. You may notice that some of these are slightly different conditions, but we can make phenols, essentially just a little bit of acid, water in there. We can make chlorides and bromides, and we can do that with copper. And in fact, you can also do it with iodine. Copper cyanide, you can put the nitrile on there. HBF4, we'll put a fluorine on there. And even just Ki, just potassium iodide, we'll put an I on there as well. Or you can use the copper iodide. I like this idea because then everything's consistent. Notice you can't just use the copper fluoride. For some reason that doesn't work, but for chloride, bromide, iodide, you can just use the copper 1 salt. For fluoride, you need HBF4. To put a hydrogen on there, H3PO2. And then finally, this last one is azo dyes. We can actually do azo dyes, which we haven't really talked about. So let's talk about that, and that will be the last reaction that we need to discuss. So again, in summary, these aryl diazonium salts, they tend to be stable. You need to keep them, like I said, kind of cold. If you start heating them up, you get all sorts of interesting reactions. Okay, so here's just some examples of things that you could make. So we could put chlorines in the ortho position to a methyl group. And that is a reaction that would actually be able to do using typical chemistry. Now, if you look at this middle example down here, that's a reaction that with our previous aromatic chemistry, we wouldn't have been able to accomplish. Because bromine is an orthopara director, chlorine's an orthopara director, so there would have been no way to actually make those meta to each other. And so the question is, well, how do I do that? Well, we can do that by starting with a nitro group. And a nitro group is going to direct meta. And so if we had a nitro group on there and we chlorinated it, that chlorine would go meta to the nitro group. And then to get the amine, we would need some way to reduce that. And so there's, again, many ways to reduce it. One of the easiest is just to use Fe and HCl. Or you can use H2 in a catalyst. Either way, it would reduce that NO2 group to an amine. So this is kind of cluttered, so let me clean that up a little bit. So we would chlorinate, and then we would reduce, and we'd end up with this metachloroaniline. We would then turn this into a diazonium salt, do a poof reaction with copper bromide, and we now have these in a meta arrangement. And again, that is a synthesis that we would not be able to do previously. So if here's some other ones. We've never been able to directly attach a nitrile to an aromatic green. So this opens up some syntheses that we wouldn't be able to perform before. In fact, here's one that we wouldn't be able to perform because previously, if we were to introduce a carboxylic acid on there, we would just use the Jones reagent. And the Jones reagent would actually oxidize both of these groups and give us a dicarboxylic acid. So if we want to make this compound here, we're going to have to use some new chemistry. And then, as I mentioned before, we never really had a decent way to make a phenol on there. The one way that we had to make a phenol back in the aromatic chapter, and I even skipped over it, actually would react with that group as well. So these two examples here, the only way that we would be able to synthesize them is by using Sandmeyer reactions. And so to do this, what we're going to do is take cumene or isopropylbenzene, and we're going to first nitrate it, HNO3H2SO4, and that would give us an NO2 here. Okay, so after that, we would do step 2, which turns that NO2 into an NH2. Iron and H3O plus would turn that into an NH2. Actually, since we're under acidic conditions, it actually would be an NH3 plus there. But that's not going to cause problems for us. And then finally, after we add the third reagent, and you just do this all in one pot, just add HNO3, H2SO4, you'd wait, add some iron and some little bit of water, and wait, and then you'd add NaNO2 and wait, and you'd end up with this diazonium in there. And that diazonium, you could then treat with CuCN, and let's draw out the product of that. So from step 1, what I would get is the nitrile para to the isopropyl group. And then, of course, just like we talked about in the carboxylic acid chapter, if I take H3O plus and heat, I can hydrolyze that nitrile to a carboxylic acid. And if we have this diazonium, like we just talked about, if we take water and heat, it converts that into a phenol. So two products that we wouldn't have been able to make by previous aromatic chemistry. So Sandmeyer reactions are very useful. Oh, here's just some other examples of things that we could make. We could make parabromo parabromotoluene. Again, we could have made that by methods that we had previously, and we could even made iodobenzene by methods that we made previously. But this example down here is, again, having a carboxylic acid and a methyl group. We couldn't have made it previously because our previous methods would have oxidized to give us that carboxylic acid, and that would have also oxidized the other alkyl groups. So the key to the Sandmeyer reactions, what it allows us to do is we have a nitrile that we don't need to oxidize, we just need to hydrolyze. And if we hydrolyze it, it gives us the carboxylic acid and leaves the CH3 untouched. Okay, let's go on. I'm gonna beat the Sandmeyer to death. So the last reaction is this diazonium coupling reaction. And this diazonium coupling reaction is really interesting. If we have a diazonium, so we made that and it's sitting in solution, and then we threw in another aromatic compound that had an electron donating group. And those electron donating groups tend to be oxygens or nitrogens. We see an interesting reaction. They couple together. So this is known as the diazonium coupling reaction. And so how does this work? Well, we can see how it works below. Notice that we have a positive on the nitrogen that we'd love to get rid of. And what we do is we have an electron donating group that's going to feed electrons into this aromatic ring. And so this aromatic ring is going to be a nucleophile. And we're going to push electrons out, attack the end nitrogen, and that's going to leave or push electrons up onto that nitrogen to get rid of that positive. Now, just like we did in electrophilic aromatic substitution, we end up with this non-aromatic compound. And so what we need to do is pull off a proton and re-aromatize. So this step right here is exactly what we did back when we did electrophilic aromatic substitution. In fact, this, you could argue, is an electrophilic aromatic substitution. We just have a new electrophile, which is this interesting diazonium compound. And so we're going to push electrons in, again, push them out onto that end nitrogen so we can release electrons to that positive nitrogen so it no longer has a positive. And overall, you end up with these diazonium compounds. They're extensively conjugated, so they tend to have colors. So this one right here tends to be orange in color. And so these are also known as diazonium dyes or azo dyes. So the key to a diazonium, making a diazonium dye or an azo dye, is you first need to make the diazonium, and then you need to introduce an aromatic group that has an electron donating. And those will couple together to make these azo dyes. And so if you vary the groups off there, you can change the color. And so this one is yellow. You can see down in the bottom here, this is known as Congo red. I'll let you figure out what color it is, but it's got huge amount of conjugation throughout this entire molecule. And so it appears red. And what's interesting is it forms hydrogen bonds with cotton, so you can actually use this to dye cotton fibers. So azo dyes are very commonly used to dye fabrics, and also a few of the artificial food coloring agents are actually these azo dyes. So in summary, what you need for the azo dyes is to make these azo dyes is you need a diazonium salt, and you need a activated aromatic group. And so again, these tend to be oxygens or nitrogens, and they tend to add to the para position. So we can see down here the mechanism. So the double bond comes out, attacks that nitrogen, kicks those electrons up. We get the sigma complex here, which again, you don't need to draw out in the mechanism, but it is showing what this oxygen does to the reaction. It actually helps push those electrons out to the para side. And then finally, to get this last step, we just have some base, pull that H off, and re-aromatize to get us to this diazonium. So in essence, this is the exact same mechanism as an electrophilic aromatic substitution. So you can make all sorts of azo dyes. So if we wanted to make the one in the box in the top right there, there's some good ways to disconnect and some bad ways to disconnect. And the good ways to disconnect is you want to find where your electron donating group is. And so I can see that I got that MEO there. And since that is going to be my activated group, that's going to be the part that I'm going to pull off, which means that the rest of this molecule is going to be the one that has the diazonium on it. So if you have a synthesis that you need to make this molecule, separate off the one that has the electron donating group, and that is going to be your nucleophile. So you can see that we're going to disconnect there. And so our two parts that we want to couple together would be those. And so the synthesis that we'd undergo is we'd need to start with this molecule right here, convert it into a diazonium using the typical reagent, sodium nitrite and HCl. And then in the second step, we would throw in our group that has the electron donating group on it. And ta-da, we've got an azo dye. So that's where we're going to end this section 22.12. We're not going to talk about, we'll visit these molecules when we get into talking about DNA, but that is the end of the chapter. So I will just scoot ahead. So we're not going to talk about any of those. Don't forget that you should know about the spectroscopy of amines. Primary amines tend to give you 2 peaks up here, where secondary amines tend to give you a single peak. If you don't have hydrogens up there, so if we had a compound that does have a nitrogen, but there is no peak in this region, it's probably a tertiary amine, because, or I guess it could be a quaternary amine. But since this doesn't have an NH to stretch, you're not going to see it in that region. So we can tell the difference between a primary and a secondary and a tertiary amine. And some NMR and mass spec. And then, again, summary of reactions. So preparation of amines that we just reviewed at the start of this lecture. And then let's go back, the reactions of amines. So what we covered today was we can acylate them, and then we can react them with nitrous acid. Primary amines with nitrous acid tend to give you these diazonium salts. Secondary amines with nitrous acid gives you an N-nitrosamine. If you have an aromatic diazonium, you can do these Sandmeyer reactions and get all sorts of interesting compounds. And then finally, you can do azo couplings. And that is it for the amine chapter. So good luck with your studying. We will have a test on Monday, and I'll post more information about that in Canvas.